right, so the recording has started. give people just about another minute to remember their login information. And important, I just remembered to make the chat available for people, so that's good.
And I should probably unmute myself at some point.
It'll make the talk significantly better to hear you. Actually, on that note, I guess it's about 3:01, so we can go ahead and get started so that we'll have plenty of time for discussion afterwards. So welcome everyone to this week's LPI seminar. We're very happy to be joined this week by Dr. Susanna Swinzer. Some of you may remember her from her time here at LPI, but Susanna is now a senior lecturer in earth science at the Open University in the UK and an expert in water rock alteration using isotopic and noble gas techniques. Susanna is here today to speak to us about a topic: assessing reaction pathways on Mars, from meteorites to sample return. If you have questions during the talk, you can write those in the chat and we'll address those afterwards, or you can wait till the end, virtually raise your hand, and I'll ask you to unmute yourself. So I think that we're all ready to go. So I will turn it over now to you, Susanna. Thank you so much for being here.
Thank you for inviting me. It's a pleasure to be back at the LPI, even if just virtually for the moment. I hope we can change that soon and I can be back in person as well. I am going to talk about reaction pathways on Mars today, and I am going to talk about the theory and the modeling. And I said from meteorites to sample return, but I'm actually also talking about some analogs. So what I will be talking about today is mainly on how do you assess the parameters that you cannot measure. On Earth here, it is usually the fluid that we cannot measure, because when you get to a geologic scene, you know what there is before any water interacts with the rock, and you know the alteration phases that result from it, but the fluid is usually gone. And even if you have the luxury to pump up some hydrothermal fluids from underground and measure them directly, they will have changed. They will have depressurized. They might have degassed. Putting those gases back in would also be a task that thermochemical modeling can do for you. But that's not as far as I will go today. Instead, I will talk about what thermochemical modeling of Earth analogs and Martian compositions can do for our understanding of Mars. A few words: Sam already introduced me as noble gas person. On the upper left, that's the, I actually have a laser pointer here. On the upper left there, that is the laboratory I got my PhD in at Max Planck Institute in Mainz. And noble gases are also important on Mars because the SAM instrument can measure them, has measured them, and probably will measure them again. We've even done argon, potassium argon dating on Mars with the SAM instrument. But there are people at LPI who can talk, and nearby JSC, who can talk about this a lot better than I can. I just say Alan Tremont, ask him if you want to know anything about either MSL or Perseverance, which is actually in the picture over here. I've worked on the Martian meteorites, mainly with the noble gases. I am part of the future ExoMars rover, which should have been on Mars by now, but the rest is history. What I am instead choosing is something for today is something that actually started at LPI. I don't know if Dave Kring is in the audience. He hired me as a postdoc to assess impact generated hydrothermal systems on Mars. And how do you do that? No rover at the time had investigated anything vaguely related to impact crater hydrothermal systems. That has changed now with Opportunity reaching Endeavour Crater and the rim there in Marathon Valley. But that was done through thermochemical modeling, and that's what got me into this. And how I used it up here as an example is a Naclite example I will be talking about, and down here is a bit of Curiosity XRD, which also will become important. But also, I want to talk about what we are doing at Astrobiology OU. Astrobiology OU is a group that it was founded 3-4 years ago, we say 5 years ago. It depends whether you think of it as started when we started to think about it or when we got the funding, which is not always the same, as you all well know. And so what we have in our group is mostly the geology, for example, habitability, biosignatures, the microbiology, limits of life, life detection. We are also looking at origin of life, but we don't stop there. We go a step further and we expand our research into things such as governance, planetary protection here, but also into social science aspects. For example, the question that one of my PhD students tries to answer: if you have a space technology and you use that to solve problems in the developing world, in the global south, what would that do? Would that actually achieve what you think it achieves, or does it not achieve what you think it achieves? And space technologies are widely used as one example in that. But back to the science, what we do here is we do a lot of simulation where we have either just the rocks and fluid and gases, and in these systems, don't know why this picture suddenly is so blurry. You can put in a gas, you can put in a fluid, and both separately, which is special to our instrument. And this is a big heating and cooling jack that you can put over all of your vessel here, so that we can achieve temperatures from almost 0 to all the way up about 300, and we can grow microbes in this, of course, only up until about 120, then they will die. And we add to that analog work, a picture of the Atacama up here and all the mud cracks and the percolates that would form there. And we do a lot of modeling. That's what my group does. And this also, as a disclaimer, only about a third of what I will be showing you today is actually the research that I did. A lot of it is done by people who work with me, and one of them is Dr. Stuart Turner. He is one of my current postdocs, Dr. Nisha Ramkisson. She set up the vessels up here, the first set of vessels, but she is also doing a lot of modeling. Back here is one of my PhD students, Robert Seidel, now Dr. Robert Seidel. And there are a couple more where I will be showing you results of what other people did, and I will point them out at the time because I don't want to give you the feeling that I did all of this by myself. No, I didn't. But let's talk about thermochemical modeling a little bit. I said you need it because you can't observe everything. If we could observe everything, and if we had a time machine to go back to when that fluid was there and could pick it and bring it to the lab, then we wouldn't need to model. So any shortcomings that you might have and might spot in the modeling, which it has, and I will point some of them out, the question is always, could you get to that information in any other way? And the answer is no. And if the answer is no, then you know what thermochemical modeling adds to your overall assessment of a situation, be it on Mars, be it on Earth. I already gave you the example that if you have water altering a rock, then that fluid is likely gone by the time you get there to observe the alteration. But that fluid would be exactly the thing that a microbe uses. So that is what actually makes your environment habitable. We all know that life needs water, but it needs a lot more. It needs the transport of nutrients to where it is, and of waste products away from where it is, or it can't live there. And then what is that fluid actually looking like? And that's the reaction between rocks and the water at its given pressure and temperature that actually defines what is in that water. What can the microbes use? Do we need sulfate reducers? Do we need iron rich scenarios? What do we actually need? So it's not only a question of can something live there, but also who can live in there? Which metabolisms are possible? And these are all questions we can answer with thermochemical modeling. But first and foremost, we can complete the story of what was going on in a given place geologically. So what can we model? Well, basically, if you take the overall amount of codes. We can start with metamorphic things. We can start with melting and crystallization. That's not what I'm going to talk about today, but that's also thermochemical modeling. We can do freezing. FreezeChem is a code that is quite widely used on Mars as well for obvious reasons. I don't do that today because I've been given 45 minutes to talk, so I need to just narrow it down. So what I am going to talk about today is mainly dilute fluids interacting with rock, and temperatures can be high. I said impact generated. I'm not doing so much volcanic, but that would of course be possible as well. Impact generated can go from any temperature. I say below boiling here. Boiling can be modeled, but introduces a whole host of new things. And the water to rock ratio matters. How much water is actually in the system? If it's very little, geologists would call the scene a metamorphic reaction. If it's intermediate, you have something like hydrothermal, and you also can have very high water rock ratios where mostly the water just transports away material. And I'll show you examples of all of them. And if you have a dilute fluid, it's a code like ChimXPT, which is underlying all except for one of the models that I will be showing you today. ChimXPT is a code based on Debye-Hückel. Those of you who are a little bit familiar with thermochemistry know that the Debye-Hückel theory talks about a fluid in the way that every ion that's in the fluid doesn't know about any other ion in the fluid. So you have a very dilute fluid where the interaction of water with the cations and anions is the only thing that you have to think about. Of course, in a more saline brine, if salinity, ionic strength gets higher, then that doesn't apply anymore. And then you would need a pizza code. And FreezeChem and Freak, these are codes that are based on the pizza approach, which can handle more concentrated brines. You can do low temperature as well. Of course, you can do anything as soon as you have liquid water up until it starts to boil. That's the range I am going to look at today. I will do some evaporation and some concentration with the caveat that the absolute proportions might not be exactly accurate, but the general direction of what forms is accurate. And I made a comparison of some of the models I did with the Chim code and had them remodeled in Freak the other day, and the proportions are slightly different in the range of 5%, but the general picture of what we get remains the same. So now, what do you need to do? You've got that code, you know what you can do with it, but that's only a very, very, very beginning. What you then need to do is you need to have a research question, because well, the world is wide open. You can calculate basically anything you can think about, but does this make sense? So having a really good research question is the first big question. But then you have that research question, you need to ask yourself a couple questions. What's the pressure and temperature of the system? What information do I have from observations such as alteration minerals in my hand specimen, in the field site on Earth, on Mars, from the rovers, from the orbiters? What is the observation that I actually have? And I need two. I need the observation of the alteration minerals, and I need the observation of what was the rock before the water interacted with it. So these are the two things, the host rock and the ultimate goal of the modeling that I need to know and assess. But I also need to assess what's actually the fluid that comes into this. Of course, water, but how did that water look like? What temperature did it have? What ions might it already have carried when it reached that site of alteration? And that, again, can be done from observations, from assumptions. A mass balance calculation sometimes help. And it's the most part of the modeling is usually spent on making sure you've got your assumptions right and making sure you know why you make the decisions you're making. Now, once you have the unaltered host rock composition, you've got the alteration minerals, you've got an idea of what the fluid looks like that you want to use, then there is one thing left to do, and that's kinetics. Some codes do assess the solution kinetics, and you can put minerals in there. Other codes like CHIM that I use, it just takes the chemistry, and they are less computing intense. You are quicker doing some models. But also dissolution kinetics is adding other problems in terms of where is a certain dissolution of a certain mineral defined, under which conditions, what are the data that you have. So if I am assessing kinetics, I usually do this independently, and I go in with a starting composition that takes that into account rather than the minerals and calculate that. So this is all the things that you need to do before you even open the code and start modeling. But then once the code runs, your thinking isn't over, because kinetic or databases are only as good as the experiments that go into it. And that becomes a problem when you get to slightly lower temperatures, because if you get to lower temperatures, a lot of our data are actually extrapolated. And why is that? Well, that is because Grant lifetime is 3 years, and reaction times at 5 degrees C is probably 30,000 years. And I can't wait that long for some thermochemical data before I can run a model. So what we need to do here is we need to take these models and see what they bring out. And then we need to go to nature and ask the question, does this mineral actually form? Nature, what do you think? And nature does these experiments for us, and we can use the entire whole host of observations that we have from geologists all around the world to assess if a phase that our computer tells us it would like to form there actually forms. And so there is a lot of iterations to say, nope, that is actually not forming. So you exclude it and you see what the code comes up with then. And that's not cheating. That's simply taking into account that our thermochemical data are done in laboratories, which have the limitations that experiments need to be done in a Grant lifetime, or at least in a human lifetime, right? And so that's some of the things that you need to do. And of course, you need to troubleshoot problems when the code runs into problems of having too many variables and that kind of thing. But that's now getting into under the hood of this way too much. And let's go back to some of the actual things that I want to present to you today. Let me start with a historic little thing. This is where it all started for me, with working with David Kring and on impact generated hydrothermal systems. And the research question that we had was what would alteration mineralogy look like in an impact generated hydrothermal system on Mars? Of course, they have been investigated on Earth. Chicxulub, where Dave worked a lot, is just one of the many, many, many examples. Unfortunately, we don't have a big crater in a basaltic system on Earth. They are usually very small, and then they have the unfortunate locations such as Deccan traps in a very warm and wet environment. So they would be a small crater with just low temperature alteration in a high weathering environment. And any mineralogist in the room knows that you can't really distinguish between a intense weathering mineral and a low temperature water rock interaction mineral, because, well, these are the same things actually for most of the minerals. So we need to look at the bigger craters, which are usually in different lithologies, more granitic, gneiss. And then we need to transfer what we know from there about temperatures, temperature evolution, about pressure, water rock ratios, and transfer that into the basaltic system. And that's what modeling is ideal for, because what you know are all the steps that you need to match. And then you take the code and says, I know what a granite does in this scenario because I can observe all the steps. Now I do it with a basaltic composition, and I figure out what are the differences, because all I have changed is the chemistry. And so what we modeled went in proper hydrothermal temperatures, as a mineralogist would define them, from 100 to about 300 degrees C. And I choose pressures high enough to avoid boiling. in this study. Of course, boiling is a study in itself, and I can talk about a few questions. I'm actually currently trying to model some boiling, but I just stay within the fluid phase for this topic and talk. So the incoming fluid is a dilute groundwater. I said we needed to think about what that water would be. So what I did is I looked at an earth example. I looked at the Deccan traps, where we have a lot of groundwaters that are basaltic dominated. However, basalts on Earth and Mars are different in one key characteristic. The iron is much higher on Mars and the calcium is much lower on Mars. So I just adjusted these compositions a little bit. And that's what I mean with modified to match Mars. I took out a little calcium and added some iron. Of course, iron is not very soluble, so you can't add very much to a solution, but that is the very dilute groundwater that I brought in. And I looked at host rocks and I looked at the Martian meteorites. Chassigny is basically olivine. It's a very, very mafic composition, which has very little aluminium. Lu 88516 has about 60% olivine, and the rest is feldspars and pyroxene. So it's got more aluminium and silica than Chassigny would have, but it's still a very, very mafic composition. And on the other end, we take DOFAR 019, which at the time in 2009 was the Martian meteorite with the most feldspar, so the most aluminium, sodium and potassium rich composition I could find, actually measured on Mars. And then I also added, just for the fun of it, Humphrey, which is a Mars exploration rover measured composition. And equipped with those 4 starting compositions, I ran models, and I start this talk now with going with just some very simple comparison results. I will show you more detailed results in later examples, but let's start to compare and understand what a water to rock ratio means and what that does to those different compositions. So I am looking here of all the models I ran at 150 degrees C. I said I choose the pressure to just be high enough to prevent boiling. And I have a very high water rock ratio of 100,000. So that is something that you would find, say, on a surface of a rock where the rain goes over all the time, on the surface of a fracture where the hydrothermal fluid just goes through all the time. So it is a very, very dilute environment where most of the cations and anions are just actually transported away. And that is reflected in the results, because all compositions, Chassigny, the olivine-rich composition in black, Lu, or the olivine-only composition in black, Lu, the very olivine-rich composition in red, DOFAR, the feldspar-rich composition in green, and Humphrey in yellow. For those of you who can't see the colors, the black is always on the left and the yellow is always on the right. So what's on top here is always on the left, and what's on the bottom here is always on the right. The order is always the same. So now what we see here is that there isn't that much difference because you only get basically the iron precipitate either as hematite, the iron oxide, or as pyrite and iron sulfide. And that tells you a little bit about the oxidation stage, because we still have the pyrite, and you precipitate the aluminium as diaspore. That's all. And we know this from Earth in very high water rock or very long exposure to fresh fluid, repeated fresh fluid scenarios. So all that is basically left here is the iron and the aluminium, not even some silica. If we go to what I call an intermediate water rock ratio of about 1,000, pressure and temperature are always the same. Color code is always the same. Left to right is always the same. What we have here is a typical hydrothermal scenario. You've got lots of water, but it's not completely overwhelming the rock, and it's not completely just transporting everything away. And now you see the differences come out. And that is because it's not just the solubility, and anything that would like to go into a fluid is just gone, but it's the rock composition that starts to dominate. And let me just point out a few things. We are at 150 degrees C, so we would get things such as serpentine, chloride, but we also still get the clays. And so what we see here, if we focus on chassigny, basically olivine only, it forms some serpentine and some chloride, getting the silica and the very, very, very little aluminium that's in that rock into there. We don't have any clays, especially not the aluminium rich clays, but we have a ton of iron oxide. And because there isn't that much aluminium, a little bit of an SiO2 phase here called quartz. It can be anything, and it can have been anything over the course of a Martian history, change into anything else and back again, because the silica phases actually can transform into each other. That's why, for the simplicity of it, I call it quartz here. So we have basically that split up in the SiO2, the silicon dioxide, and the hematite, the iron oxide, with a little bit of other minerals indicating our temperature. If we go to the other extreme end and look at this screen now, we see that we don't have any serpentine or chloride, but that we form a lot of non-tronitic clay. And that is because we've got enough aluminium. Also, we form some kaolinite, and especially that non-tronitic clay is observed on Mars, even already from orbit, which was already known in 2009. And we've seen a lot more of these iron-rich non-tronitic clay minerals from the ground as well. We still get some hematite, we still get some pyrite, but we don't have any excess silica anymore. That all goes into kaolinite and hematite. And the Humphrey composition is pretty similar. It's got a bit more iron and a bit less aluminium, so it's got a bit less of the clays and a bit more of the iron oxide, but that's about it. Now, looking at what would happen if we have even less water at the same temperatures, what you then get is what would be a metamorphic composition, even forming garnet maybe at these temperatures, but certainly some amphibole, some serpentine, and you see that a lot more serpentine is formed when you have less water, and everything is skewed towards the more metamorphic assemblages. I will be focusing on the hydrothermal assemblages mostly, but not solely. And what can we do with this? Well, what we can do with this is we can apply it to a real geologic scenario. We can put together what we know about an impact crater, because that was our research question. What type of minerals would we expect in an impact crater? So let me show you an impact crater. And the crater is taken from a book by Richard Grieve, and the temperature information from Abramov and Kring 2005, as well as the water flow. So this is the crater. We've got a crater rim here. The diameter, think of it as 150, 200 kilometer diameter, something like Gale or bigger. And what you have here is the crater rim. You've got a central uplift, and I've got something that's somewhere in between a central peak and a central peak ring. What is important here is not the exact structure, but is how the underground would look like. So the underground would look like very fractured here, because you've got slumps and slides when you form that crater rim. So you've got these deep reaching fractures here, but you've also got a lot of fractures, especially deep reaching fractures around the central uplift here. And that's because that material just came upwards. And so these are the areas where water flow is most intense. But you, of course, also have fractures in the entire crater. You've got a melt sheet, which is initially impermeable because it's very glassy and it's very hot. And so is the middle point here, because the central point of a crater is heated above 360 degrees C, which is the transition zone between ductile and brittle of basalt. And if it's ductile, the fractures just can't open. And so what will happen eventually is that this will cool and the water will move in here. But if we are just a couple hundred years or 1,000 years after the impact, when the water flow is at its most vigorous, you will not have water flow in the very central part. I will now go through these 6 boxes and look at what's actually happening in them. So start up here. We've got a fracture that comes from deep down, transporting hot water up. reaching the surface. So what we will have is this sudden depressurization, sudden temperature change, and any of these fluids carries a lot of excess SiO2. So you can always expect SiO2 to precipitate. And you might also get some hematite, especially along the fracture walls where you have a lot of water flow. That would be the most high water to rock ratio scenario I showed you earlier. Now, the next step you have is you look at this fracture itself. And if you have a basaltic rock and you have a lot of water, then you will find mostly hematite, but also smectites, especially as the water penetrates into the rock and according to the permeability. And permeability really is key here. A rock can be as porous as it wants to if it's not permeable. Permeability is key here. And that's why the fractures enhance that so much, but also why there's always a gradient into the rock where you get some hematite, where the water flow is at its most vigorous and most leaching happens, and where you then start to form the smectites adjacent to that, where the water flow isn't as vigorous and where the water rock ratios get lower. Now, next, let's have a look at that melt sheet. That melt sheet, I said initially, is impermeable. However, it will become permeable, and from terrestrial melt sheets, we know that they get a lot of vug fillings. And these vug fillings will be at the lower water to rock ratio, and because it's not that permeable, especially initially. And so you get zeolites and other minerals that are typical for the low water to rock ratio scenarios, but mostly typical vug filling minerals such as zeolites and things like that in basaltic environments. Now, if we are looking at the region below the crater where there aren't that many fractures, but you still have water flow from the fluid that's coming back into the crater after the impact, and it's getting heated more and more towards the central part, which I told you is the hottest. So then you get the chlorite and the serpentine with or without amphiboles and garnet, depending on how your water flow is actually looking like. So this is a very, very complex scenario, and it's only getting more complex because the more you get to the central part, the more you will get the higher temperature end of the mineralogy. I only showed you one temperature in the interest of finishing the talk in time today. And so I have the smectites here, but you might even have much, much higher temperature alteration initially and then overprint that again. So with a real rover on the ground, if we can access areas like this, we would have to look for the whole host of things. And as Ellen will tell you, we haven't found any of that at Gale Crater because it's filled with sediments, and we have a blast of a time investigating all those sediments and reading the book of history here in terms of how Gale Crater has been filled. We haven't found any of that yet, although any of the impact scenarios yet, although we've got some evidence at least for slightly higher temperatures, for example, in sulfur isotopes. But that aside, the central uplift part is the most important and most interesting. And when you get into that zone of really high temperature, you would expect that you have very pervasive alteration, that you have the most high temperature alteration there. I've got a little tiny sliver of talc down here to indicate that. But you also have very vigorous alteration. So that would be the part where if I were on foot, you could go there and I would go there and I would investigate that, because that's where the most variation would be. But of course, you then need the infamous thin section that we haven't invented on Mars yet, because you need to get into a lot of detail and you need to do what we only can do with modeling right now, assess the different stages and the succession of events. And once you have all of that, you can actually go a step further. And now here's the first piece that I didn't do myself. Nisha, who I pointed out to you earlier, Nisha Ramkison, who is a postdoc in our group, she took the rock nest composition from Curiosity and a hematite slope from the MER missions and redid that modeling that I did basically at different pressures and temperatures. But what she also did, and why she basically also redid that modeling, she made physical analogs of that chemistry, and they are chemical analogs. So if any one of you does experiments and is interested in chemical analogs, give me a shout, because they are physically available for experiments, and we've used them in experiments. And in parallel to those experiments, she did some modeling, and she found very much the same things. Sorry for the different color code here, but she assessed the very same things, a few more further out, and but assessed the very same things that I assessed at the time. And she found, of course, unsurprisingly, a lot of the same minerals. Nontronite in purple here, the one on the very right for those missing here in Rocknest, but chloride, and she has 100 degrees C here, and that's the example I picked from her paper. But she then took this a step further. With every little bar and color that you see here, behind that there is a reaction. And that reaction you can describe, for example, an olivine turning into a serpentine, an olivine turning into some nontronite plus a little bit of quartz. All of these things you can assess step by step, reaction by reaction. And from that, using modeling again, you can extract the energy, the delta G, that this reaction would actually provide if intercepted by a microbe. And what she then did is she calculated the biomass that you could theoretically sustain, in this case, just from all the reactions involving some iron and some redox change of iron. And you could sustain 10 to the 9 to 10 to the 13 cells per kilogram of dissolved rock. And that is pretty much similar to what you would find on Earth. So this is an assessment of, yes, Mars is habitable in theory. We've got water, we've got all the ingredients, but here's a number that you can actually point to and say, this is how many cells this crater in a basaltic environment as found on Mars could sustain. And with that, now let's look at a few other scenarios that are not big impact craters at 150 degrees C. And I'm going back to another impact crater first, but hey ho, they are interesting. Because what I haven't looked at now are all these volatiles. CO2 is something of a conundrum on Mars, because there is the thick CO2 atmosphere. It should be there, yet we have found very little carbonates. Perseverance in Jezero crater will hopefully traverse to an area where we saw carbonates from orbit. So that's something to be looking forward to, and that we are currently trying to model in what could be the reaction pathways there, what would be the kind of microbial communities that could be supported in that scenario. But there are also the halogens, fluorine, chlorine. It's someone who shared their postdoc time with me at LPI, Dr. Justin Filiberto. Not sure if he is on the call today. He's now at JSC, right next door to LPI. He looked a lot into fluorine and chlorine, and we modeled some Gusev crater and Gusev crater successions involving fluorine and chlorine. But of course, there is the sulfur-rich compositions. The Curiosity rover has found sulfate veins basically from day 1 of the mission, or say day 30 of the mission. And that is important on Mars. MER already found them, and every rover lander since has confirmed that. And so they are all very important for habitability, because sulfur is another redox active element. Fluorine could be actually an antibiotic in some sense. Chlorine is very important. And so having these reaction pathways, knowing what these elements do, is critically important for the habitability, for the microbes that live there. And I am now going to show you results from a couple of things that I did with Justine, and then here in the UK with John Bridges from Leicester University, just up the road. And so what we have here is the same Gusev crater composition. We are talking about Humphrey again. And so modeling this rock at 150 degrees C, that's kind of my favorite temperature. and avoiding boiling, 110 bar probably, but avoiding boiling. What you get if you do not have CO2 is a very, very complex scenario. I promised you to show you all the wiggly lines and a full set of results. So let me introduce that diagram to you. I've got the water rock ratio on the x-axis, and the 100,000 that I showed you earlier is just on that right line. The 1,000 that I also showed you earlier is here in the middle, and then we have a water rock ratio of 1 on the very left. So I picked earlier this, and this scenario, and I will kind of look at them again, because at the very high water rock ratios, what we have is hematite, that red line. So we again see most of the things are actually dissolved away. We've got the hematite, we've got the pyrite, and we've got diaspore, the familiar things from the model earlier. And at a water rock ratio of 1,000, we still have some hematite, we still have the pyrite, but now we get clays such as the kaolinite, we get some nontronite again, and we get some chloride. And you see that this is kind of a transition zone where we go from a lot of nontronite into a lot of chloride. We are getting quartz at some point, especially when we are getting serpentine. And then we again have a metamorphic composition down here with some amphiboles and lots of chloride. The entire picture changes if you put 0.5 mole of CO2 in there and keep replenishing it so that the fluid always has 0.5 mole of CO2. So now you basically have a partial pressure of CO2 in there that's pretty high. And that means it would change everything. And that's why I say carbonates is kind of a conundrum, because the carbonates would be dominating it all. So if we have a lot of CO2, why don't we see a lot of carbonate? And I don't have an answer to that yet, because the answer could be it was there and it's gone now. The answer could be it didn't ever form because most of the reactions didn't happen in contact with that CO2-rich atmosphere. But just wanted to point out there is a huge difference when you have a lot of CO2 in a system. And if you have less CO2 and you bring in a fluid that has a fixed amount of CO2, you will only get CO2 in the very beginning and it will get exhausted. But so what you see here is really CO2 in the system as a partial pressure always present. And that might not be what happens in nature. You might maybe have it here at the very high water rock ratios and then not when it has reacted because the fluid is actually not in contact with the atmosphere anymore. But these are thoughts that we can discuss in the discussion section. What I want to show you now is focusing on a water rock ratio of 1,000. How do these fluids actually look like? And are there differences in these fluids? And so the next diagram that I will show you mainly different CO2 and different temperatures, because CO2 is a gas, and unlike any other species or many other species, gases get less soluble with higher temperatures because they simply degas. So there's a bit of a difference here. Let's look at this. So what we have here is all the elements on the x-axis that I want to look at in the fluid, and we have the concentration in gram per kilogram of water. And what you can see here is chlorine is dominating, but that's also kind of how we set up these models, making assumption of chlorine, and it's justified because of all the perchlorates that you see on Mars. So the fluids will have been chlorine rich. But you see that the next abundant element is the sulfur. And you then have, of course, very little aluminium, because that's just not very soluble. And then depending on what you have in that solution, you have some iron and magnesium. And calcium less than you would expect if you are familiar with fluids like this on Earth, because simply there isn't that much of a supply on Mars. And the same holds true for potassium and sodium. One thing that I want to point out here is fluorine is actually quite temperature sensitive, and at higher temperature goes into solution much more. But of course, fluorine is also sensitive to things such as what is the phosphorus amount that you actually assume, because apatite isn't very soluble. So if I had a bit more phosphorus than I had in this model, and I'm now coming back to how important it is to make all of these assumptions before you even start to model, then I would probably take down a lot of this calcium and take out a lot of this fluorine. I had the phosphorus as per the Martian meteorites. That might not be actually quite as accurate anymore after we found quite some phosphorus rocks on Mars. So I might revise that and to take into account the full set of phosphorus concentrations that we now know 10 years after I did that on Mars. And with that, what can we do with this? We can again put this onto a geologic scenario. And this is now a Gusev crater scenario, which would have, like every crater, started with a lot of hot and heated rock, the target rock seated, melt and melt breccia sheets and ejecta blankets, all hot basalt, basically. And then you have the water that interacts with it. And you get a first set of altered target rocks, because all of this water that goes through would form these minerals that I showed you earlier. And again, the deeper you get, the more permeable things are, the more water you have. There are notable differences that we've talked about in the earlier figure. But then you have a second alteration when the whole system cools after that initial high temperature phase at maybe 150, 200, 300 degrees C, or maybe even above that, and maybe you see some boiling. You will cool down the system and you will have a very long phase of alteration around 100, 90, 80 into diagenetic temperatures around 50. And that will overprint the things again. In Gusev itself, we have that basalt that then didn't get altered, but it only got eroded, which means it couldn't take part in much of all the water rock reactions. If you take a crater like Gale, you would have sediments in here, but that's based on the observations that rovers made. And then you, of course, have erosion, you have more incoming fluids, you have sediments, fan deposits, and they all get altered as well, because you've got minerals that come in. And now we are in the realm of diagenetic alteration. And I'll show you some results from the diagenetic alteration in Gale later on. And they would be fairly similar to what we have here, because they are based on the general Martian soil assumption. Now, going back to something where we have a lot more chance to observe details. I said the infamous thin section, because alteration is a very, very spatially resolved thing. And being that spatially resolved, we actually need to look into how can we make observations on millimeter and sub-millimeter scales. And that's one of the examples, and I'm starting to go faster through the examples now, because you know a lot of the principles. What we have here is 1, 2, 3 observations where we have an olivine host rock, and we see the dissolution. You see that olivine gnawed at surface here. And then we get some sideritic carbonate, we get some clay, and we get a gel phase, which actually has the composition of the clay. Pulling this out here, what we have is the olivine, the carbonate, the clay, and probably something that's just frozen clay. And we've also got pyroxenes up here. And you can see how it is different. The olivine would just supply iron, magnesium, and silica, while a pyroxene would also supply aluminium and calcium. And then there's the mesostasis, which doesn't supply iron, but supplies a lot of silica, aluminium, and also the sodium. And so depending on what dissolves at which given stage, you get different results. So if we assume the Nakla rock is hit by a hot fluid after, say, a small impact into, or some post-magmatic, but we assume a small impact into the cooled off stream, magmatic stream. So we get a hot water and we have CO2 filled hot water. What's first to react? Well, it's the olivine. And when the olivine reacts first, you get a sideritic or anchoritic composition, depending on how much of calcium you assume in your composition. And we can model that. And what we find is a pH of 4. And iron is mostly 2+, and the water rock ratios are actually fairly high. But you dissolve some of the mesostasis and some of the pyroxene with a huge bias towards dissolving the olivine. So say 70% of the olivine and 20 and 10% of all the rest. But now if the fluid evolves in that system, water rock ratios get smaller, the rock will keep dissolving, but the carbonate, of course, doesn't take silica, aluminum, sodium, and potassium. So that will get enriched more and more, and you will put more and more rock into the fluid. And then water rock ratios gets lower. And what I found is I could match these observations of non-tronitic clay with some certainty, actually, at a very low water rock ratio of about 6. And I have mostly smectite here. That's the dark line up there. I've got some serpentine. That's the dotted line down here. And the carbonate is kind of still present, and some trace phases. So that is what you can actually do when you have observations that are like that. And that then would, of course, give you a much better handle on the details of the fluid and the fluid evolution, of which I've just pulled out the iron and the pH here, which is actually around 9 at the end, and mostly iron 3+ because the iron 2+ is found in the minerals. So you have a redox change and a pH change. If we now go to Gale Crater and apply all that we have learned to the observations that are possible there, because we've got a lot of really valuable information from Chemin, from SAM, from the multispectral, we've got the chemistry from APXS and ChemChem. So we've got a ton of information, but we don't have the microscopic detail of the alteration assemblage that I talked about right now. And so we need to make some assumptions from analogs and the meteorites, and we take an amorphous phase, which we cannot find out in Chemin what that actually is. And for the purpose of these models, I assumed it is a volcanic glass and put the composition in there as dissolving composition. Of course, there are other assumptions, but let's take it like this because I use the Rocknest sand shadow, which doesn't have any clay. And diagenetic temperatures, 50 degrees C. We assume clay formation. Clays are a problem. And I've just looked at the time. I don't get into that now. And I also did some evaporation models. So what we find here is we've got these drill holes with loads of information about them. And we've got the portage soil, which is the sand shadow that's up here where we scooped some. And we've got the Cumberland and the John Klein drill holes. And they are similar, but characteristically different at 50 degrees C. Water rock ratios, again, in this case, from 100,000 to 10, shown here. And all that I want to take away is we get loads and loads of clays. We get chlorite, we get non-tronite, we get some serpentine, we get loads and loads of clays in these scenarios. Details are in our paper because I need to rush this a tiny little bit. You can do evaporation. We found a lot of sulfates on Mars. And when you do evaporation with that fluid, you've got a problem. And that problem is you've got a fluid that contains a lot of silica. I said earlier, silica is always in an overabundance in these fluids. So you would get something that is a dirty sulfate, which especially initially wasn't observed. So when you get this and you dump everything out that is in the fluid by just simply evaporating this, you start with quartz and then you get the sulfates, and pulling out the little corner here now, you also get things such as calcite and halite and all the rest of it. However, it would basically be in one place, which we didn't observe initially. We now have more dirty veins where you could come up with successions, but initially, the first model was you dump all of this in an evaporative scenario, and then you redissolve it, and you basically recrystallize it, leaving the silica down low and only taking the sulfate up into the veins that were observed through another evaporative scenario. We've now got a lot more, and I point you towards Alan Freeman for I talk about this, because he's actually on the Chemin team, or ask Liz Rampey from next door. We've got a lot more information about the clays, and Stuart has, one of my postdocs has modeled especially the Vera Rubin Ridge and below clay formation and clay and hematite formation. And the moment you get hematite, what that really means on that diagram of water rock ratios versus mineral abundancy, again, you get out of that water rock ratio of 1,000 non-tronite only. That's what we saw down here at Yellowknife Bay and what I modeled. And you got into the more hematite-rich scenarios, specific, of course, to the host rocks that we assumed. But what I want you to take away here is that water rock ratio actually plays a really important role in controlling the phases that you get. Now, very quickly, in the last probably 5 minutes, I see Sam is getting nervous a little bit. What we can do is we can go to Earth and we can make these observations on Earth. We can then develop a model pathway, and that model pathway can then be applied directly to Mars. And I've got 2 examples. It's the San Rafael Swell in Utah, which my student B. Baharia does currently works on with Dr. Filiberto from JSC next door, a former postdoc as well. And the Waschenbach Gabbro in Germany, where a former student of mine, now Dr. Robert Seidel, with some German collaboration worked on. So this is the beautiful landscape in Utah and all the people who contribute to that study. I'll give you a second to just read all the names. And B has provided me with these beautiful, beautiful slides, which show real field pictures down here and pictures where she actually drew, like, this is the field picture, this is the drawing, this is the field picture, this is the drawing. And what I want to point out here, what we are doing right now, and invite her if you want for the full talk, probably in a couple of months' time, she's just writing up. We've got these dikes which have sulfates in them, and these sediments around are very sulfate rich. So this dike intruded into a very sulfate rich environment, and then you get the sulfates transported into cracks in this dike. You get amphiboles altered to first carbonates, then sulfates. Lots of replacements going on here. And you have that rim with the alteration zone, and of course the alteration that goes outwards from here. And just as a very high level summary, what B is currently doing, and check out her LPSC presentation in March when she is giving that, or have her around. She is modeling all of these reaction pathways to assess the fluids. What are the volatiles? Can these fluids support life as we know it? And how would that look and transfer to Mars? Another example, very quickly, is the Frankenstein Gabbro in Germany. It's a very, very large igneous complex, which is a gabbro. And what we have here is we can actually compare this at this scale. We could do the knacklight work. And here's everyone involved in the study. And what we can do is we have that infamous thin section. You see the 250 micron down here. And we can look at the ceratization of these feldspars. We can look at the pyroxenes, which alter to pyroxene and actinolite. Here's the plagioclase, and we can look at ceratization, at epidote forming, and this is this is actually an element map where you can see these things that I just pointed out to you in beautiful detail, and you can see how the plagioclase here, which looks like plagioclase and thin section, is actually replaced by a K feldspar. And then you can go through the different steps that we cannot observe on Mars just yet, and can say we have a first phase that actually is a ceratization at a high temperature. We can then go to the next phase, zoom in again, and can say we've then got the calcite forming, including some sulfides such as galena and the chalcopyrite over here. And then finally, we have the third phase in hairline fractures, and the last phase where we have some chloride forming, some epidote forming. And you can put all of this together, and I'm focusing again on a beautiful drawing that puts all of these steps together, and you can discern that reaction pathway and then plug it into Mars, and you can actually model quite well the different scenarios of how these especially hot water rock interactions would happen. And you see 250 degrees here, and then things such as non-tronite, they are just gone. You get the high temperature phases, you get a chlorite, but you get a lot of feldspars, you get garnite, so you get a very different looking epidote forming a metamorphic scene here that looks very different. It's something that we haven't yet discovered on Mars, much apart from in fluid and melt inclusions. Last but not least, you can control your environment, you can go into the lab, and you can do all of this, but it's short term. I showed you, and here I actually have a better picture of this. I don't know why the other one turned out so blurry. This is our laboratory equipment controlling the gas and the fluid in two different inlets and measuring what the fluid looks like constantly, the minerals at the end of the experiment. And so we can take what we know from the field, plug this into the biotic and abiotic weathering experiments, do the thermochemical modeling to expand our time scale, because laboratory experiments are usually 30 days, 60 days, maybe half a year, but there is the funding problem as well. And then we combine what we know from this dual approach. We know what nature does. We know what the laboratory experiments do, especially with microbes, which have lifetimes and life cycles of about 30 days. And we can use all of this, again, with some of our, you saw the rock nest earlier, that's the regolith analog that Nisha did. And we can put that in there and assess a brine composition, assess a microbial community. This is actually another analog site, the River Dee estuary here in the UK. And we can put all of this together and make these experiments and find out, how do actually these brines look like? What are the differences between something that doesn't have microbes and something that has microbes? And can discern some biomarkers, some potential biomarkers. What do we need to look for if we are looking for potential habitable scenarios? What would the microbes have altered in these rocks? What would be the differences? And we can assess all of this, and we can model both of these things. And I'm rushing a little bit here because I want to get to that diagram. And that's what we can do in the lab. You have three different things here, and I'm focusing on the potassium here. It's the time, and it's the potassium in this case in micromole per liter. Aluminium, iron, magnesium, calcium, manganese are all also available. But what you see here is in green, the microbial growth curve. So you see after about 400 hours, microbial growth stalls and is fairly constant until we stop the experiment. And that's just the number of cells, because this is cell counts. The community itself might change because conditions change. And then you have the aluminium in the abiotic experiment in yellow, and the biotic experiment, the potassium in the biotic and abiotic experiment. And you see that especially towards the end, they start to be actually different. And if you look at the magnesium, they start to be even more different the longer the experiment goes. And that is because microbes do something to the precipitates, and microbes also take up some of these elements, making them unavailable to precipitates. And we can reflect that by modeling these things, and mainly by keeping the pH at what the microbes would keep them at, because they are pretty good at controlling their environment. Here the pH is running free. And you see characteristic differences of what precipitates. Magnesium does not go into anything precipitated at any scale. You see this in the constantly increasing line, such as the potassium. In the biotic experiment, in the abiotic, magnesium actually precipitates. So we have a simpler secondary mineral assemblage. We don't have nontronite, for example, and in the biotic experiment. And that's what we actually observe. And so last but not least, in a summary, and I've talked for over an hour now, sorry, Sam, what we know is habitability needs water, but that's just like the beginning of it. We need that energy source. I showed you that we can actually calculate that. We need look at the environments. They are really, really specific. What can survive there? How much of cells can be supported? Because there are microbes that can't deal with any oxygen. There are microbes that need oxygen. There are microbes that can't deal with much sulfur. There are microbes that need sulfur. And so it goes. It's the whole biology that we can actually assess, and where thermochemical modeling helps us to say what's actually in this solution. What can they actually use? I haven't talked about trace elements, but they matter too. Debarati Das, now Dr. Debarati Das, did a lot of boron and lithium modeling with me, and she is actually at McGill in Canada, so I was just a collaborator, but I was heavily involved in the modeling that she did, and they matter too. Get her and talk to you about that. So it's a very, very complex story that I tried to condense into that hour that I now talked. And we added experiments and observations in analog experiments to fully understand what it is that we are modeling here and predict those reaction pathways for current and future Mars exploration. And with that, I say thank you very much. This is actually Perseverance, and I hope it doesn't think like this, but that's me done. Thank you.
Awesome. Thank you so much, Susanna. For those of you who may need to run, you can write your questions in the chat box before you go, and we'll get back to you with some of those answers. But we can take a couple of minutes, I think, to address some of the questions. And if you do have a question, you can raise your hand. I see we've got some applause, also virtual applause from the audience. So we have one question here from S.J. Ralston. When you say water to rock ratio, are you referring to a physical water to rock ratio, such as the mass of solid rock to water, or a chemical ratio, the mass of dissolved rock to water?
That's an excellent question. And I actually took out that slide because I already found I'm talking way too long. And I've stopped sharing now for the moment. I hope that's okay. So water to rock ratio needs to be defined very, very stringently. And there are actually different definitions hidden in what I've been talking about. So one water to rock ratio, if I talk at the water to rock ratio in the model, it's always the amount of water in kilogram and the amount of dissolved rock in kilogram, or gram in this case. So it is a direct comparison, weight for weight, of water to dissolved rock. If we are talking experimental water to rock ratio, usually people are talking about, I've got a beaker, I put a kilogram of water in there, and I've got rock, and I put 100 grams of rock in there. And that's their water to rock ratio. But that isn't the actual third version of a water to rock ratio, because of course it's a valid measure. They've measured it just by putting it in there, right? But not all of this rock will take part in the reaction. So I have 3 water to rock ratios that I normally define. It's the model water to rock ratio, which is very easy. I know what I've done there. It's the experimental water to rock ratio. It's also very easy, but very, very, very different. And those two are actually linked by the reacted water to rock ratio, which is really hard to assess. If you were to pick out one of these grains that the experimentalists put into the beaker, take it out, make a cut through it, you will see that only the rim has reacted, but it's not uniform. It's a gradient, and the more soluble things might be leached a lot deeper into that grain than the less soluble things. So the water to rock ratio, the real water to rock ratio, might not even be the same for elements such as potassium and sodium, or for elements contained in easily dissolvable minerals, compared to minerals that are less easily dissolvable, or elements that are less prone to go into solution. So this is a very, very complex story. The way we overlap them is via the potassium. So we generally compare the potassium content of our measured solution, especially if we have microbes in there, because the potassium is the only thing they don't like to eat. And it's also something that doesn't go into that many minerals. So that's the way we compare those two ratios via the dissolved amount of potassium in the solution, and then compare that to the dissolved amount of potassium in the models. Very good question.
Great, thanks for that answer. So if other people have questions, they can raise their hand or unmute themselves at this point, or write a question in the chat box. So you had mentioned, that ideally, of course, we could get like a thin section of one of these impact generated hydrothermal systems. So is that something that is being planned for some of the Mars sample return missions, or are we fighting for that, or do we know?
Well, Alan would know much better than me because he's actually on the Perseverance mission.
Ooh.
And probably some others as well. But let me say this. I would ideally, of course, get one of these samples, but they are even hard to come by on Earth because the samples that are actually preserved are usually deep down somewhere. So we would need to drill. And that's a very hard thing to do. So the best thing I think we can do is get a really good understanding of the rocks that are there. And any rover can do that. Curiosity did it, Perseverance, the MER rovers did it. Look at Marathon Valley and what we learned there already about impact generated hydrothermal systems. Because what we can observe is at least the whole of the alteration assemblage and the rocks that were there initially. And then we can go to Earth. We can use craters such as Chicxulub, Houghton, and all these craters, the big craters on Earth that we can actually look at in great detail. And we can then take the thin sections there and say, this is a typical reaction pathway, and assume that the physics of an impact generated hydrothermal system are the same. And then we can take the chemistry and model the terrestrial case with the terrestrial chemistry, and then plug out the terrestrial chemistry, plug in the chemistry of Mars. And that's basically the Waschenbach story that I started to tell you, but in the interest of time, then just cut a little short. We can take out Earth, plug in Mars, and use the very same modeling steps. And that way we've got the physics from Earth combined with the chemistry from Mars. And if that then ideally matches the mineralogy that we find in a lump on Mars and not teased apart in the thin sections, in these different steps, we have a good assumption of what this actually looks like.
Okay, great. Thank you. That's fascinating. I wonder, like, even taking it another step out from precision, you know, like looking at a lump of rock and then saying, even if you have even lower precision, if you want to look at materials from, you know, remote sensing data or something, could you even, I mean, obviously there's a whole layer of complexity added to interpreting remote sensing data, but, and I guess it would depend on the extent of alteration of materials and things like that, whether or not it would be detectable. But is that, I guess, something that people do or is done or is a target?
I guess that's where it all started, because the first study I did was mainly looking for nontronite and the clays, because that's what actually had just been observed from orbit. And so just understanding that and what are the temperatures, what are the water rock ratios, was a big step back in 2009, because we didn't have any ground truth. The Opportunity rover was far away from Marathon Valley in 2009. I think they reached there in, now I'm looking at who is on here, who was on the mission, 2012, something like this. So the more we learn, the better. But orbital data are fantastic because the orbital data give you the overview. When you look at orbital data, you can look at the distribution. There is a paper by Bethany Ellman where she looked at the central uplift of an about 20-25 kilometer diameter impact crater. And what she can map there with a CRISM and the HiRISE together is that you actually have big lumps of rock in that central uplift which aren't altered, and then in between you've got this chloride, and then she has patches of silica, and you can match all of this up and you can map it, and then you can go with what we know from Earth and can put it on that crater I showed you in the beginning and say, if you have patches of silica, you probably had a fracture reaching there. And so that's what we model. That's what we can put together with the orbital data. And if you have chloride, that probably comes from way low down and is a much lower water rock ratio eroded to that level now. And so it is that combination of all these pieces of the puzzle that I find so fascinating about this.
Yeah, that is actually just absolutely fascinating. So thank you for that. I'll give anyone else a chance to ask a question. I know we're a bit over time now, but this has just been absolutely fascinating, Susanna. And Honestly, if you hadn't said something toward the end of your talk, I was so entranced that I would have not have noticed what time it was. So
Thank you for that. And no, sorry for overrunning a little bit. I got carried away on my Kratos.
understandable. Well, if there are no more questions, or if you do have some, you can send it to Susanna during another venue. But we just want to say thank you again so much for coming and sharing your work with us. That was absolutely fascinating. So thank you for being here.
Thank you for having me. And it's always good to be back at the LPI, even if virtually.
Yeah, well, hopefully we'll see you here in person sometime soon.
Thank you.
All right, thanks everybody. We'll see you in a couple
Bye.
of weeks. Have a great Thanksgiving or whatever holiday you may be celebrating next week. All right, thanks everybody.
Thank you.
Close out the meeting. Actually, I don't think they made me host, so we're just gonna have to leave this thing open for whoever is gonna eventually close this.
Thank you. Have a good one.
All right,
Bye.
thanks, Susanna. See you later.